All right, so here's a problem we just discussed a little bit in class. So we have a little bit different kind of load here. This is a trapezoidal shaped distributed load. We're going to assume that we have a pin connection at A and a pin connection at B for this strut at DB. And we also talked previously about the fact that this element here, since there's no applied load, and it's pinned at each end, that this is a two-force member. In fact, when we later today, or definitely on Thursday, when we start talking about trusses again, basically this is just a truss element. It's either going to be in compression or tension. So we know the direction of the member, the force, but we don't know its magnitude. So the first thing I want to do is draw a free body diagram for this section A, B, C. So I'll come over here and draw the line. At A, which is a pin, I'm going to assume two unknowns, AY and AX. As we talked about before, I don't even think about it. I just assume up for Y and to the right for X. And then we'll come over here to B. And I'm going to assume that I have a force in the line of action of member BB, and I'll just call that force B. If you look at the drawing, this was 60 degrees, this is 90, so this angle should be 30 degrees. So I know the orientation, I just don't know the magnitude. You can already count it up that I've got 1, 2, 3 unknowns. I'm going to have 3 equations of equilibrium for this body. I should be okay. Now, how am I going to deal with this trapezoidal load? I know the area of a trapezoid. I can find that. That's easy. I don't remember off the top of my head the centroid of a trapezoid. So what I like to do is break this up into 2 objects. This is what superposition will allow you to do. So I'm going to first look at the rectangular portion of that load. I can find the area of a rectangle, and I know the centroid of a rectangle. So what is the area under that rectangular portion of the curve? Well, it's the base, which looks to be 9 meters, and the height, which looks to be 2 kilonewtons per meter. So that's going to be, what, 18? 18 kilonewtons. And where's the centroid of a rectangle? Right down in the middle. So I'm going to come in here and draw my 18 kilonewton load. And I'm going to see that's, what's it, 4.5, right? Yes. So I'll just say 4.5 meters from the left right now. I also know this distance is 4.5. I'm not filling that in because I'm going to have to deal with this triangular part. So let me get a different color. In honor of Mardi Gras, I'll do it in purple. By the way, the Mardi Gras season has started. Anybody been celebrating? Every day. I like that. Okay, so what's the area of a triangle? 1/2 base times height. 1/2 base. 9 times, what is the height of the rectangle, of the triangle? 2. That's a common mistake. People will see this and just say 4. It's not 4. Right? You've already knocked off 2. So just don't forget to account for that. So it looks like it's 2 divided by 2 times 9 is 9. And where is the centroid of a triangle? Yeah, just remember 1/3 or 2/3. I always like to go 1/3 from the big end, tall end. So 1/3 of 9 is 3. So this would be 3 meters. So what would this space in between be? 1.5. Everybody see that? So again, there's your free body diagram, and you're really halfway home. Now you just have to get out your 3 equations of equilibrium and turn the crank. So what should we do first? Should we sum forces in the x direction first? Yeah, that would. I have one x force here. Oh, and I've got an x component of this. One equation, two unknowns. I could sum forces in the y direction. No. So this is a good problem to emphasize that if you go to the pen and some moments about A, you should be able to solve for B. So let's do that. I'm going to sum moments about A. Now when I do that, I'm going to need components of this B force. So let me just sketch that one in. And that's going to be B times the sine of 30 degrees, right? Everybody see that? I didn't leave myself much room in there, but there would also be a bx, which is going to be b times the cosine of 30. So now I'm ready to roll. Who did I leave off on? Miss Higgins, I think you're up. Some moments about A for me, and just with the known forces first.
So it's -9 kilonewtons.
Correct. What's the moment arm?
That's 3.
That's correct. Sorry, that doesn't look like a 3, but that's a 3.
And then it's -18.
Correct.
And then, 7.5.
Ms. Dasgupta, what's the reaction, the moment of the B about A?
Would it be the cosine of no, it'd be b sine 30.
Is it positive or negative moment?
Positive.
Okay, so the force is B sine 30. And what's the moment arm?
4.
Sorry?
Oh, it'd be the proof. It'd be 9.
Oh, wait, I think it's 6.
Oh,
I messed up. This is 6, and then the little extension is 3. I forgot to add those. So 6, yeah. So somebody solve that for B for me. I think it's going to come out positive. Mr. Mabry, did you get that?
36.
36 exactly? Wow, anybody else get 36? Okay, cool. And that's kilonewtons. Now it came out positive. What does that mean? I assume the right direction. Now think about that. Is that, put that element in compression or tension? Do you remember that? So if it's pushing up here, it must be equal and opposite on the element. So that means it's pushing the element, which should be pressure. Don't worry about that now. We'll talk about that in more detail. I just want you to start maybe thinking about it. Right now it doesn't matter. I assume this direction, and I got a positive result, so that's the correct direction. Ms. Pinafore, what do we do next? Or what do you want to do next on this problem?
Some of the forces in the Y.
Some of the forces in the Y. Let's do that. Mr. Drum, sum the forces in the Y for me.
Got A of y plus b sine 30 minus 9 kilonewtons minus 18 kilonewtons.
That sounds pretty good to me. Anybody else see anything? Do we lose anything? So we got these two forces going down, so that's negative, up, and up. Now, we know B, right? So you can just plug that 36 right in there. You should be able to solve for AY. I'll just throw this question out. Anybody? Mr. Robinson, you know what AY is?
It's 9.
9? Anybody else get 9? You're just shaking your head.
It's 9. Yes.
Are you like Rain Man? Can you do these calculations without a device?
No, I was working them out.
Oh, wow. Very good. I didn't see any fingers on calculators like your buddy there. So it's 9?
Yes.
Positive?
Positive. Yes.
Excellent.
Dr. King,
Yes.
I know you already said it, but can you explain
Well, let me draw it off to the side here. So this is the bottom of the beam, and I assumed B was going in this direction, right? And we knew that this was 30 degrees. Now, I think it's always easier to break a force down into its X and Y components, right? Because when I do that, it makes finding the moment arms a lot easier. So I want the Y component. So when you're looking at the triangle, right, that Y component is this side. You see that? So when you're calculating sine, the opposite side of the angle is given as the sine. The adjacent side of the angle is cosine. So this one should be sine 30. And then this one should be what? Be cosine 30. And we're going to need that later. Well, not later. Actually, pretty soon. Because that's the x component, right? Did I do that wrong? Did that help at all?
Yeah, I think I was just.
Dr. Camp, what did AY be negative?
I don't know. You guys tell me. Is AY negative? I think not. Why is it not negative? Let's see, B is 36. The sine of 30 is 0.5, isn't it? So that would be
Okay.
yeah, that would be 18, and then that cancels that, and 9. Is that the way you solved it?
Yep.
Wow. I'm bringing some toothpicks tomorrow for you. Okay, so let's go back and finish the problem. Who did I leave off on? Oh, you have a question, Mr. Stewart?
No, you got the problem.
Oh, I did? Okay, well, what do we do next, Mr. Stewart?
Stop for the forces of x.
How do we do that?
So you assume the forces of x equals 0.
Correct. So I'm going to assume to the right is positive. Mr. McClanahan, do that for me.
You got AX plus B cosine.
That is correct. Everybody see that? Why is this element positive? Because you'll notice it's to the right. Everything to the right to me is positive. So what is the solution, Mr. Andrews? Or anybody else who's out there? Say that again, 31.2? Anybody else get that? Does that make sense? See, I assumed AX was to the right, so actually it's pushing. But it's negative, so it actually means it's pulling. Does it make sense that this connection needs to pull to the left to keep this thing in equilibrium? I think it does. If you notice all these forces acting down, it's trying to rotate clockwise. So we've got to have something to pull back. And there we go. Any questions about that one? That one took us a little longer because I got you guys.